Welcome to Ultimate Sleep Doctor. Tonight, we'll delve into a realm of extraordinary connection. Let's explore the fascinating world of quantum entanglement, a concept where particles, separated by vast distances, remain intrinsically linked. It's a secret of the universe, a whisper of interconnectedness hidden within the fabric of reality. Think of it as a profound echo, a gentle reminder that we are all part of something far grander than ourselves. Perhaps contemplating this interconnectedness can ease the anxieties of the day. Let your thoughts flow like the currents of a quiet stream. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe, let your thoughts drift. Let's begin. The story of quantum entanglement began not with a quiet laboratory, but with a vigorous debate, a clash of brilliant minds wrestling with the very nature of reality. It all started in 1935 with a paper published by Albert Einstein, Boris Podolsky, and Nathan Rosen, collectively known as the EPR team. They weren't trying to discover entanglement. They were deeply troubled by its implications, a concept that seemed to fly in the face of everything they understood about the universe. Quantum mechanics, newly emerging from the work of Niels Bohr and Werner Heisenberg, described the world in terms of probabilities and wave functions, where a particle could seemingly exist in multiple states simultaneously until measured. This was unsettling, but the EPR team found the concept of hidden variables, undetectable properties that determined a particle's state, a much more palatable solution. Their argument centered around what they called locality, the idea that an object can only be influenced by its immediate surroundings. They believed that if you could measure a property of a particle, you should be able to instantly know that property of its entangled partner, no matter how far apart they were. This implied a kind of instantaneous connection, a spooky action at a distance, as Einstein famously called it. They reasoned that if quantum mechanics was complete, it should be possible to describe the properties of a particle without disturbing it. However, the act of measurement, according to quantum mechanics, did disturb the system. This, they argued, revealed a fundamental incompleteness in the theory. They formulated a thought experiment involving two particles prepared in an entangled state, with each particle having either spin up or spin down, essentially, a clockwise or counterclockwise rotation when measured. The EPR team devised a scenario where an observer, let's call him Alice, measures the spin of one particle. Based on the quantum mechanical description, the outcome is random. But they argued the other observer, Bob, who measures the spin of the other entangled particle, must know the result of Alice's measurement instantly, violating locality. They believed that if a complete theory existed, it would predict which properties a particle could have without disturbing it. This created a paradox. If the particles were truly independent, knowing the state of one wouldn't instantaneously tell you the state of the other. The initial reaction within the scientific community was largely skepticism. Many physicists, including Bohr, found the EPR arguments unconvincing, arguing that the paradox arose from a misunderstanding of quantum mechanics. The debate raged for years, fueled by the competitive environment of the time as physicists raced to establish their theories. However, in 1964, physicist John Bell took a crucial step. He realized that the EPR argument could be formalized into a mathematical inequality, now known as Bell's inequality. Bell's theorem showed that if local realism, the combination of locality and the idea that particles have definite properties, were true, then certain statistical correlations between the measurement outcomes of entangled particles would be limited. Any violation of these limits would prove that at least one of these assumptions must be false. Experiments began, most notably those conducted by Elaine Aspect and his team in the 1980s. They used rotating mirrors and sophisticated detectors to measure the correlations between the spins of entangled photons, essentially testing Bell's inequality. The results consistently demonstrated a violation of the inequality, providing strong evidence that local realism was indeed incorrect. This meant that entangled particles were indeed connected in a way that defied classical intuition. It was as if the universe itself was subtly guiding the outcomes, independent of distance. Accepting this non-locality has profoundly shifted our understanding of space, time, and information. It suggests that the universe isn't always as straightforward as we perceive, and that connections can exist beyond our traditional notions of causality. The story of entanglement continues to unfold, a testament to the power of questioning and the ongoing quest to understand the deepest secrets of the cosmos. Let's explore a fascinating aspect of the quantum world, entanglement and the peculiar property of spin. At the heart of it lies a fundamental characteristic of particles, like electrons and photons, called angular momentum. Think of it like a tiny, invisible spinning top, even though these particles don't actually spin in the way we're familiar with. This spinning motion, this angular momentum, possesses a property called spin, and it's quantized, meaning it can only take on specific, discrete values. These values are usually described as spin up or spin down, representing the orientation of the particle's spin along a chosen axis. Now, how do we create pairs of entangled particles with correlated spins? One common method involves generating entangled photons. We can use a process called spontaneous parametric downconversion. Imagine shining a laser beam through a special crystal. This crystal, through a process that's surprisingly random at its core, can split a single photon into two photons that are entangled. Crucially, these two photons will always have opposite spins, one spin up and the other spin down. This isn't because they were predetermined. It's a consequence of the fundamental quantum relationship they share. We can also entangle electrons through interactions. For example, if two electrons are brought close together and then separated, their spins can become correlated. The exact mechanism can be quite complex, involving the exchange of virtual particles, but the result is a pair where if one is measured as spin-up, the other instantaneously becomes spin-down, no matter the distance between them. This instantaneous correlation is what makes entanglement so puzzling. The key to understanding this is the concept of quantum superposition. Before a measurement is made, a particle exists in a combination of all possible states, in our case, both spin-up and spin-down simultaneously. It's not that we don't know its spin, it's genuinely in both states at once. This state is described by a wave function, a mathematical representation of the particle's probability distribution. When we measure the spin of one entangled particle, the act of measurement forces the particle to choose a definite state, either spin up or spin down. This is called wave function collapse. Simultaneously, the other entangled particle instantaneously collapses into the corresponding state, maintaining the correlation. This isn't faster-than-light communication, though, because the outcome of the measurement on the first particle is random. We can't control whether it's spin up or spin down. To describe the statistical properties of these entangled states, we use something called a density matrix. It's a more sophisticated mathematical tool than the wave function, providing a way to represent the probabilities of different measurement outcomes. The Born rule, a cornerstone of quantum mechanics, dictates how to calculate these probabilities. It tells us that the probability of measuring spin-up is related to the square of the amplitude of the wave function describing the spin-up state. Let's consider an example. Imagine two entangled photons, photon A and photon B. If we measure photon A to be spin-up, we know with certainty that photon B will be spin-down. Conversely, if we measure photon A to be spin-down, photon B will immediately be spin-up. The mathematical relationship governing this correlation is deeply embedded within the wave function of the entangled pair. This seemingly instantaneous correlation, defying our classical intuitions about space and time, remains one of the most fascinating and debated aspects of quantum mechanics, offering profound insights into the very nature of reality. It's a reminder that the universe operates according to rules far stranger and more beautiful than we might ever imagine. Let's explore a truly remarkable frontier in science, quantum computing. At its heart lies a phenomenon called quantum entanglement, and it's far stranger and more powerful than anything we experience in our everyday lives. Classical computers, the ones that run your phone and guide you to your destination, store information as bits. A bit can be either a 0 or a 1, like a light switch that's either on or off. Quantum computers, however, use qubits. A qubit isn't just 0 or 1. It can be 0, 1, or both at the same time. This is thanks to the principle of superposition. Think of it like a spinning coin before it lands. While it's spinning, it's neither heads nor tails. It's in a combination of both states until you observe it. Qubits, similarly, exist in this blurry state of possibilities. Now, entanglement takes this even further. When two qubits are entangled, they become inextricably linked, no matter how far apart they are. Measuring the state of one instantly determines the state of the other, a connection that seems to defy distance. A quantum computer uses these entangled qubits to perform calculations. Instead of a single, linear process like a classical computer, a quantum computer operates on many possibilities simultaneously through what's called a quantum circuit. This circuit is a sequence of operations that manipulates the entangled qubits, transforming the input information into a solution. The beauty of this is that the computer explores a vast number of potential answers concurrently. Some quantum algorithms are specifically designed to take advantage of entanglement. Shor's algorithm, for instance, is designed to factor large numbers, a task that would take even the most powerful classical computers an incredibly long time. Grover's algorithm is used for searching unsorted databases, dramatically speeding up the process. But building a practical quantum computer is incredibly challenging. Qubits are extremely sensitive to their environment. The slightest vibration, temperature change, or electromagnetic interference can cause decoherence, the loss of their quantum properties, and the breakdown of entanglement. This is like trying to maintain a delicate balance, easily disrupted. To combat decoherence, quantum computers require incredibly precise control and isolation. They're typically housed in ultra-cold environments, often cooled to temperatures just above absolute zero, colder than outer space. Cryogenic cooling systems are essential, and sophisticated control systems manage the qubits' states with immense accuracy. Error correction is also a major focus. Scientists are developing methods to detect and correct errors that arise during computation. Interestingly, the principles of entanglement also play a role in a theoretical process called quantum teleportation. While not transporting matter, it allows the transfer of quantum information, the state of a qubit, from one location to another instantaneously. Different types of qubits are being explored. Superconducting qubits made from tiny electrical circuits are currently a leading technology. Trapped ion qubits, using individual ions suspended in electromagnetic fields, offer high stability but are more complex to control. Photonic qubits, using photons, particles of light, are another promising avenue, offering potential for long-distance quantum communication. Quantum computing research is progressing rapidly. While a truly universal, fault-tolerant quantum computer is still years away, significant breakthroughs are being made in qubit stability, control, and algorithm development. Scientists are optimistic that within the next decade, we may see quantum computers tackling specific problems like drug discovery, materials science, and financial modeling, with unprecedented speed and efficiency. It's a remarkably exciting time to be exploring the strange and powerful world of quantum entanglement. Let's explore a truly remarkable way to send secret messages, one that relies on the strange, wonderful properties of quantum entanglement. It's a process called quantum key distribution, or QKD, and it's built on the idea that uncertainty itself can be our greatest protection. Imagine two parties, Alice and Bob, who need to exchange a secret key. Instead of sending the key through a regular channel, where a sneaky eavesdropper might intercept it, they use entangled photons, particles of light that are linked together in a mysterious way. When Alice creates pairs of entangled photons, she randomly sends one photon to Bob while keeping the other for herself. Each photon can be in one of two states, we'll call them 0 and 1, but until she measures it, it exists in a combination of both at the same time, a concept known as superposition. The act of measuring forces the photon to choose a state. The beauty of entanglement is that because the photons are linked, whatever Alice measures, Bob instantly knows. Alice and Bob then both measure their photons, recording the results. They publicly announce the measurement bases they used, the methods they employed to determine the state of the photon, without revealing the actual measurement results. This is where the BB84 protocol comes into play. It's a fundamental QKD protocol that uses multiple measurement bases to generate the key. The key itself isn't the measurement results, but the basis used for those measurements. Now, let's consider eavesdropping. If an eavesdropper, let's call him Eve, tries to intercept and measure the photons, she will inevitably disturb their quantum state. Because of the no cloning principle, meaning it's impossible to create an exact copy of an unknown quantum state, Eve's attempt to measure will change the photons, introducing errors. Alice and Bob can detect these errors during a subsequent public comparison of a subset of their measurement bases. These errors are critical. They indicate Eve's presence. QKD systems incorporate quantum bit error correction, sophisticated techniques that attempt to mitigate these errors. However, The fundamental security comes from the fact that any attempt to observe the quantum state inevitably alters it, leaving a detectable trace. A different protocol, the E91 protocol, leverages the entanglement directly. In this case, Alice and Bob share entangled photons and perform measurements on them in a way that is intrinsically linked to the entanglement. This offers a more direct and robust security advantage against eavesdropping. Currently, the distance limitations of QKD are a significant challenge. Photons traveling long distances experience signal loss, and the generated entanglement degrades over time. To overcome this, scientists are developing quantum repeaters, devices that can amplify and regenerate the entangled photons, extending the range of secure communication. The underlying mathematics of QKD is a fascinating blend of quantum mechanics and information theory. Quantum mechanics provides the fundamental principles of entanglement and the inherent uncertainty in measuring quantum states. Information theory, on the other hand, deals with how to efficiently encode and transmit information, ensuring the secret key is securely generated and distributed. QKD's potential impact on cybersecurity is enormous. It offers a truly secure way to transmit keys, immune to even the most powerful computers. As interest in deploying QKD networks grows, we're edging closer to a future where sensitive communications are protected by the very laws of physics. It's a journey into the heart of quantum mechanics, a journey toward fundamentally safer communication. The universe holds some truly remarkable secrets, and one of the strangest is called quantum entanglement. It's a concept that makes our everyday understanding of space and time, how things connect and how far apart they can be, feel a little bit off. Scientists have been tirelessly working to understand this phenomenon, and through a series of incredibly clever experiments, they've built a very strong case for its reality. It all began with Elaine Aspect and his team in the 1970s. They designed a fascinating setup involving pairs of photons, tiny packets of light, created in a way that linked their properties, specifically their polarization, essentially, the direction in which they vibrate. These photons were then sent in opposite directions, separated by several kilometers. The brilliance of Aspect's experiment lay in rotating the apparatus while the photons were in transit. Changing the orientation of the measurement tools shouldn't have affected the outcome, yet the correlations between the photons' polarization remained, defying the idea that each photon possessed a definite polarization all along, dictated by its initial creation. This result strongly challenged the long-held local realism paradigm, which assumed that objects have definite properties regardless of observation, and that influences can only travel at or below the speed of light. Following Aspect's groundbreaking work, John Clauser and Stuart Friedman continued to refine the experimental design, using more sophisticated equipment to reduce potential errors. They meticulously tested different measurement settings, pushing the boundaries of what was possible with the technology of the time. These additional experiments further solidified the evidence for entanglement, demonstrating that the correlations were far too strong to be explained by any conceivable local interaction. More recently, scientists at the National Metrology Institute of China, NMI, have been achieving incredible distances. They've successfully demonstrated entanglement between photons traveling over hundreds and even thousands of kilometers, a truly astonishing feat. These experiments aren't just about distance. They're about the statistical consistency of the correlations. The NMI team and others are constantly refining their systems, using ultra-sensitive detectors, devices capable of measuring incredibly faint signals, and employing advanced error reduction techniques to minimize any possibility of undetected local interactions. These efforts involve complex optical systems, precisely controlled lasers, and sophisticated data analysis. These ongoing experiments aren't just confirming the predictions of quantum mechanics, which, frankly, are quite strange. They are also forcing us to reconsider our classical intuitions about space and time. If two particles can be perfectly correlated across vast distances without any apparent connection, it suggests that the universe is far more interconnected than we previously thought. The challenge now is to build technologies that can reliably harness this connection, potentially leading to revolutionary advances in communication and computation. The ongoing research at the NMI and similar endeavors worldwide represent a significant step towards unlocking the full potential of this extraordinary quantum phenomenon. Let's explore a fascinating trick of the quantum world: quantum teleportation. It's a concept that often appears in science fiction, conjuring images of instantly appearing across vast distances. However, the reality, as revealed by quantum mechanics, is far more nuanced, and frankly, less about beaming people and more about transferring information. At its heart, quantum teleportation leverages the peculiar connection created by entangled particles. Imagine two particles, linked in a special way. No matter how far apart they are, their properties are correlated. Measuring the state of one instantly influences the state of the other. The process begins with a third particle, Alice's particle, that we want to teleport. This particle exists in a superposition of states, meaning it can be in multiple states simultaneously until measured. Now, Alice performs a measurement, specifically a Bell state measurement, on the entangled pair and Alice's particle together. This measurement doesn't reveal the state of Alice's particle directly, but it scrambles the information associated with it, creating an entangled state between the remaining particle and the one held by Bob. Bob, who has one of the entangled particles, then performs a measurement on his particle. This measurement, combined with the results of Alice's measurement, which he receives via classical communication, a standard email or phone call, allows Bob to reconstruct the original quantum state of Alice's particle. It's crucial to understand that Bob isn't creating a copy. He's using the correlated information to recreate the state that existed on Alice's original particle. Mathematically, this is described using the density matrix representation of quantum states. The density matrix allows us to represent the superposition of states in a way that captures all the probabilities associated with different measurement outcomes. Essentially, the Bell state measurement collapses the superposition, and the density matrix describes how the information is transferred and recreated. Now, let's be absolutely clear. This isn't the instantaneous transport of matter. It doesn't violate Einstein's theory of relativity because the information transfer is still limited by the speed of light. Bob needs Alice's classical communication to complete the process. Furthermore, the original particle at Alice's location is destroyed in the measurement process. It ceases to exist in its initial state. The concept of no cloning plays a fundamental role. The no-cloning theorem states that it's impossible to create an identical copy of an unknown quantum state. Teleportation doesn't violate this theorem because the original state is destroyed in the process. A new state is created, but it's based on the correlated information rather than a duplicate. Despite these limitations, quantum teleportation holds immense promise. It's a key component in developing quantum communication networks, where information is transmitted with unprecedented security. It could also be used to build distributed quantum computers, where quantum computers are linked together to tackle incredibly complex calculations. The technological hurdles are significant, maintaining the delicate, entangled states, controlling the measurements with extreme precision, and scaling up the process. Nevertheless, scientists are making progress, exploring different types of qubits, superconducting, trapped ion, photonic, and pushing the boundaries of what's possible. Quantum teleportation is a powerful demonstration of the strangeness and beauty of the quantum world, a testament to the possibility of manipulating information at its most fundamental level. The universe, at its most fundamental level, likes to play tricks. It's governed by rules that seem to defy our everyday experiences, and one of the most fascinating of these rules is quantum entanglement. Two tiny particles, linked in a special way, can share a connection regardless of the distance separating them. But this connection is incredibly delicate, like a shimmering bubble easily popped by the slightest disturbance. This fragility is what we call decoherence, and it's the biggest challenge in harnessing the power of entanglement. At its core, decoherence arises from the interaction of a quantum system, like a photon or an electron, with its environment. These environments are filled with vibrations, temperature fluctuations, and even electromagnetic fields. Each of these interactions acts like a tiny, insistent nudge, subtly altering the quantum state of the particle. Think of it like a perfectly balanced spinning top. Even the faintest air current will eventually slow it down and cause it to wobble. Similarly, any interaction with the environment introduces noise, random disturbances that disrupt the delicate quantum coherence. A photon, for instance, might absorb a stray photon from the surrounding light, instantly changing its polarization. Or an electron might interact with a nearby atom, causing its spin to flip. These aren't simple collisions, they are fundamental changes in the quantum state, effectively destroying the entangled link. The more interactions a quantum system experiences, the faster decoherence progresses. Time itself is a factor. The longer a quantum state exists, the more susceptible it becomes. Distance also plays a role. The farther apart the entangled particles are, the more susceptible they are to environmental influences. So, how do scientists try to protect these fragile connections? Isolation is key. Researchers build incredibly sensitive experiments, often deep underground or in specialized vacuum chambers, to minimize external disturbances. Cooling systems are used to dramatically reduce the thermal energy of the environment, slowing down the vibrations and temperature fluctuations that contribute to decoherence. Precise control over electromagnetic fields is also critical. But even with these measures, decoherence remains a persistent threat. That's where quantum error correction comes into play. This technique involves encoding information redundantly, adding extra copies of the quantum data. Think of it like a carefully designed puzzle. If one piece is missing or distorted, the overall picture can still be reconstructed. Quantum error correction uses multiple entangled particles to detect and correct errors caused by decoherence, essentially rebuilding the original quantum state. The importance of maintaining entanglement is particularly pronounced in quantum computing and quantum communication. In quantum computers, entangled qubits, quantum bits, are used to perform incredibly complex calculations. In quantum communication, entangled photons are used to transmit information securely. But because of decoherence, these systems are incredibly sensitive and require constant monitoring and correction. Scientists are continually developing new techniques to combat decoherence, pushing the boundaries of what's possible. It's a fascinating race against time and the universe's inherent tendency to disrupt delicate quantum states, a constant reminder that the most remarkable secrets of the universe require meticulous care and unwavering dedication. The universe, as we've come to understand through the intricate dance of quantum mechanics, isn't always governed by the straightforward rules of our everyday experiences. The phenomenon of quantum entanglement throws a particularly fascinating curveball at our intuitions, and its implications stretch far beyond the laboratory into the realm of profound philosophical questions. At its heart, entanglement describes a connection between two or more particles, no matter how far apart they may be. When you measure a property, like spin, of one entangled particle, you instantly know the corresponding property of the other, a correlation that seems to defy the limits of space and time. This immediately confronts us with the concept of locality, the idea that an object can only be influenced by its immediate surroundings. Einstein, along with Podolsky and Rosen, famously challenged quantum mechanics with what became known as the EPR paradox. They argued that if quantum mechanics was complete, it must allow for local realism, the belief that objects have definite properties regardless of whether they are being measured, and that no influence can travel faster than the speed of light. Entanglement, they believed, indicated that quantum mechanics was incomplete, missing some hidden variables that determine the particle's properties beforehand. The instantaneous connection, the non-locality, suggested by entanglement caused significant debate. If one particle's state is determined instantly by the measurement of the other, even across vast distances, does this imply a connection that transcends the constraints of space? Some interpretations, like the many worlds interpretation, propose that every quantum measurement causes the universe to split into multiple parallel universes, each representing a different possible outcome. In this view, the seemingly instantaneous correlation isn't a violation of locality, but rather a reflection of our existence within one specific branch of this infinitely branching multiverse. The implications for our understanding of spacetime are truly startling. Classical physics assumes that space and time are a fixed, unchanging backdrop against which events unfold. However, entanglement suggests that these concepts might be far more fluid and interconnected than we previously imagined. Perhaps the very act of measurement, the interaction of a conscious observer with a quantum system, plays a fundamental role in shaping reality itself. It's important to remember that quantum mechanics, at its core, describes probabilities, not certainties. The entangled particles do know what state they will be in until measured. Rather, the measurement forces them into a correlated state. This challenges our notions of causality, the idea that an effect must follow its cause. If two entangled particles can seemingly influence each other instantaneously, does this mean that cause and effect, as we understand them, are not always linear. Exploring these ideas requires a willingness to question our most deeply held assumptions about the universe. The quest to understand quantum entanglement isn't just a scientific endeavor. It's a journey into the very nature of reality itself, encouraging us to consider the possibility that the universe is far stranger and more beautiful than we could ever have imagined. It invites us to contemplate the limits of human perception and the profound mystery at the heart of existence. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds one peaceful night at a time. We've journeyed through the fascinating realm of quantum entanglement facts, peaceful sleep learning, discovering connections far beyond our everyday experience. Now, let your thoughts drift, calm and unhurried, like gentle waves upon a still sea until sleep finds you. Good night.